Another example using these energy equations in order to deal with problems that are two-dimensional. So we've got a crate, we've got a force applied, it's a 100-kilogram crate, two forces getting applied to it. So we're going to have to consider the work done by all of the forces, and it just wants to know, determine the distance it slides to attain a speed of 6 meters per second. So, I always say so, sorry, I shouldn't say so often. So let's make, there we go, said it again, 800 newtons. So let's just draw on the forces we have. With a pen you can actually see. So we've got 800 newtons this way. Now, let me just think about this before I gung-ho go ahead. Rather than do that, we're going to have to figure out the components of this. So it's traveling, you can see it's on a surface, it's going to be traveling in the x direction. So in reality, we're going to be wanting the components of these forces. So we'll just draw the components onto the free body diagram. We'll use components of force in direction of travel. To find u, and so therefore we need to find those components. So maybe I'll just call this one excuse me, F1, call this F2. So F1x is going to be 800 cos 30, which is equal to 800 cos 30, 692.8. F1y, we're going to need that, although it's not in the direction of travel, but we are also going to have friction in this problem, so we're going to need the normal components to figure out the friction. Is 800 sine 30, which is going to be 400. That's newtons, this is newtons. So F2x, so we've got a 3, 4, 5 rule, so it's going to be 1000 divided by 5, 200 times 4. So it's 1000 divided by 5 times 4, which is going to be 800 newtons. And then F2y, it's 1000 divided by 5 times 3, which is going to be 600 newtons. And usually in any problem I would give, both of these will be angles. I don't use these 3, 4, 5 rules in my exams or in my questions, but this is taken from a textbook. So where are we going next? Let's just start putting things onto our free body diagram. We're going to have, so remember the free body diagram doesn't show anything except the object or objects that you're interested in. The objects being joined together has to be a rigid body, but so we're going to have 692.8 newtons. Come in, F1y is 400 newtons. At the other end, we're pulling the x components 800 newtons. And the y component 600 newtons. Then what else have we got? We're going to have a normal force somewhere. Don't know where it is, but don't really need to know where it is. Could calculate it if you did all your moments about a point. It's going to be, so that's going to be our normal force. We'll figure out what that is in a minute. We've also got gravity acting on this. Acting on the centroid. Make that a bit big. mg, or let's just call it w, or mg, whatever, it's given us mass, so we'll just do mg onto the centroid of that. And we know this thing, well, we don't know how far it's traveled, but we know what speed it's got. So I've just written that down here. I've turned them blue somehow. And so at this position, time 0, v naught is 0. It told us it was at rest to start with, I think. Yep, K is originally at rest. Determine the distance it slides to get a speed of 6 meters per second. So it's going to get to 6 meters per second at some time, t1. And the distance it's traveled is going to be 6 meters, did they tell us? No, 6 meters per second. We're trying to figure out the distance. So we're trying to figure out that distance x. And we should probably show our axes. Maybe we call this x1. Okay, the displacement at time 1. And so probably draw our axes. So that is the x direction. Positive to the right, y is this way. Now, so essentially you're getting no motion in the vertical direction, so this normal force must balance all of the vertical forces, and so you got no motion in the y direction, no motion in y direction. So therefore, the sum of the y components, force y components, must be equal to 0. So we are going to get, or you can just think about it in terms of this normal force must balance these other forces. But anyway, let's do the sum of the y components. So we're going to have negative 400 down 400 newtons from that first component. Negative mg, we probably should have just figured that out, but that's okay. Negative mg plus 600, all the vertical forces, nope, plus n is equal to 0. So therefore that normal force is equal to 600. This is going to be minus 400, so that's 200. Take away, it's going to take it to the other side, so it's going to be minus 200 plus the mass was 100 kilograms times gravity, 9.81. So it's going to be, does that make sense? Let me just double check that. Yeah, so it's going to be minus 200 plus 100 times 9.81. 781 newtons. 781 newtons. And we can figure out, oh, we forgot something in our free body, or I forgot something in my free body diagram. Don't know why I'm blaming you. We need the force due to friction. So we can figure out that the force due to friction is the coefficient of kinetic friction times n, which is going to be, is it 0.2? 0.2. So it's 0.2 times 781, which is equal to 156.2 newtons. 156.2 newtons. Now we've already split this up into the components, so to figure out the work done, these forces that are vertical, perpendicular to the direction of motion, so this one, this one, this one, this one, they are doing no work because there is no displacement in those directions. We are just interested in the work done by the other forces. So let's just write out our equation first. So the sum of the work done by all the forces is equal to a half m v1 minus v naught. v1 squared minus v naught squared. Please note that that's not the same as v1 minus v naught all squared. Different thing. I'm sure they told you that at school. And so let's get that sum of the work done by all the forces first. So that's 692.8 force, this force here, it's in the same direction as the displacement. And so therefore we are going to get 698.8 692.8 times, we don't know what that displacement is, times x. What else have we got going on here? Then we've got an 800 Newton force plus, it's also in the same direction as displacement, so it's a positive work done, plus 800 times x minus, because looking at the friction now is in the opposite direction, so it's minus 156.2 times x. Have we got any other forces doing work? We've done the 800, we've done the 692, and we've done the friction, so it looks like we're there. It's going to be equal to half times 100 was the mass of this thing, times, now v naught squared, it was at rest to start with, so this is just going to be v1 squared. And we also know what v1 is, don't we? So it told us we want to make sure that v1 is equal to 6 meters per second. So this is going to be 6 squared. So let's figure all that out. So we're going to go 692.8 plus 800 x's minus 156.2 x's is equal to 1,337 to 3 to 4 significant figures is equal to, x is equal to 50 times 6 squared, 50 times 36 is equal to 1800. So x is equal to 1800 divided by 1,337, 1800 divided by 1,337, which is equal to 1.35 to 3 significant figures meters. I think that's answered the question. So what I'll do is I'll just pause it for a second. I'm just going to check that using the equations of motion. I'll give it a quick check, and then I'll come back if I get it right. If not, I'll show you what my corrections were. So let's just write down the answer first. So crate will travel. Travel 1.35 meters to reach 6 meters per second. So I'll just do the quick check using the equations of motion, then I'll be right back. So check that using the equations of motion and the Newton's second law. So you're basically using kinetics and get the same answer, so it can be fairly confident this is correct. So for these ones, in fact for all of the ones we've done so far, we could have solved all of them just using the equation of motion and the kinetics or Newton's second law. What we're going to do now is just have a look at some problems where it's actually easier if you start using the energy equations. Makes things a bit easier, certainly a bit clearer. So we'll look at that next.